All right, I clicked the button. We're live. We're ready. Here to roll. What a crazy football weekend. I tell you, at least on the NFL side. Um, I know this weekend I'm excited because playoff start for college ball. Super excited to have A&M in there. I know there's a lot of controversy around. Okay, I guess there is just about every year. It's so political. Anyway, it's not why we're here. It was a fun football weekend, especially for the NFL. Um, the Bills, like, not to insult any Patriots fans, but that was it. I haven't seen the whole game, but I saw some bits of it. Wow. Anyway, if you're not in the U.S., none of this probably means anything to you, and that's okay. All right, hey, how you doing, everybody? I see you there. How you doing, Michael? Explain York YK Titan Chiller. So um on the YK Titan, all right. So just the YK. What exactly are you wanting explained? If there's something more specific I could get into, that would help me. So yeah, go ahead. Feel free, everybody, to throw your comments and stuff into the feed here. I'll start getting to everybody. And keep in mind, like entry level questions, stuff like that, completely welcomed, fully open to discussing anything we need to. Like, this isn't just for high level advanced chiller type questions, okay? This stream is genuinely meant to help answer your questions from the bottom up and get you the support you need, maybe bridge some gaps that you're struggling with, whatever the case may be. That's why we're here today. That's why we're going to take the time to do this in the first place. Uh, I will make a note that I've been saving up for a framework laptop. Okay, so if you don't know what those are, super cool company, fully repairable. It's one of the things I've hated about laptops for such a long time. And my mouse ended up just finally busting to the point of no repair, and then my RAM started to fail on the one I've been using for some time. And uh, I finally just I made the move and got it. So what I've actually done is I've reconfigured everything to run on that laptop. Um, and today's going to be the first official stream on it. We're going to see how it goes. I want to know, like, is the audio sounding good? Video looking fine on your end? If there's occasional glitchiness, that's probably more to do with the internet than the laptop. But any feedback you have, if you see anything weird, and if you're into, like, if you're a tech head like me and you're into computers and stuff like that, and you don't know who Framework is, I've been following them for a few years now. I do highly recommend go check those guys out. Like, if you're into repairability and being able to just keep your same stuff, uh, way into that. It's why, like, on the desktop side, I don't buy off the shelf. I've got a fully custom built desktop. Why? Not because it's cool or I'm gaming or anything like that, because I don't do that stuff. I got it because I can fix it. And when it breaks, I just fix what I got to fix, and that's good. Um, I wanted the same thing for my laptop. Anyway, they're not cheap. I'll warn you with that. Like, if you want to do an apples to apples, Framework is not cheap, but for my view of it is you make that initial investment, then as things break, and they will, especially with kids in the house, you just fix it. Anyway, uh, awesome. Thanks, Michael. Yeah, this one, I'm excited about it. Okay, I love new toys, so I'm playing. I'm playing today. I'm having fun. Let's go with our first question. All right, we're gonna roll into this. Like I said, any questions in the comments, feel free to get them in there. I will jump into those as well. If I'm trying to get into working chillers, what are some basic things I should know? Hmm. This is going to come back to a fundamental principles perspective, okay? And let's come over here to the whiteboard. And some of these things may seem a bit obvious, but I'm going to list all this out so that we really cover this. So basic information. All right. Understanding saturations. Okay. Your saturations is huge because we use it so heavily. Now, you do and technically should use it heavily throughout all the other equipment if you have any kind of training at all, which to the point of the question, yeah, get into chillers. So I'm assuming you're coming from a place of you've already got some industry background, understanding, knowledge, whatever the case. One of the things I find though is not everybody is as deep on this subject as they probably should be to do this work. And what that does is it can really make it challenging to understand certain things. So really getting a strong grasp on how saturations work, why they work, not more than just a value, right? So we can get in our head that, okay, I want to be above freezing saturation on my coil so that I don't freeze the coil. Okay. And I know that I want to be somewhere in the 40 degrees in a lot of cases in terms of saturation on my evap so that I dehumidify. Okay. And my condenser saturation needs to be, or it's going to be above a certain amount over ambient. Okay, right? So you want to use 20 degrees, 30 degrees, whatever the case. Right? So we get these kind of numbers, but actually understanding why those numbers are what they are and what they represent. They're not just arbitrary things that engineers kind of pull out of their butt. Like these are actually intentionally chosen, engineered values that have a purpose. They have meaning. And it comes back to those heat transfer rates, efficiency. Like there's a lot of in-depth information to understand here. So really get an actual understanding of saturations if you don't already have it. If you can't explain on a detailed scale, why does it matter that we run the saturations we do? Beyond just, well, we got to dehumidify. Well, it's not that simple because think of it in a chiller world. First, how do we define a chiller? It has a hydronic evaporator. That's what we have as a chiller, meaning that the fluid going through the load, the liquid, is water or brine, and that water brings the heat back to the chiller, and then we process the heat into the chiller's refrigerant stream and back out. Whereas a DX system, the refrigerant is directly in the load space. So, okay, let me scale back my terms here. I'm sorry. With an air handler, in a regular RTU or split system, the refrigerant is in the coil. That's absorbing heat directly from the load being the space. If we're in a comfort cooling, specifically the most simple application here, if we're in comfort cooling, we're taking heat out of the air. In a hydronic system, we're taking it is water that is taking the heat out of the air and then sending that heat to the chiller to then get rid of the heat somewhere else. So we need to dehumidify no longer applies. That's part of my point. If your understanding of saturation on the evaporator side is we need to dehumidify, and that's kind of the baseline of what you've built your understanding on. Well, with the chiller circuit, we're no longer, like the refrigerant itself is not dehumidifying. The water does in the coil, sure, but that's a different topic. They're connected. Don't get me wrong. They're still connected, but this is a big topic. I hit this so heavily because in all my years of training this material, this has always consistently become a sticking point for so many people. So I hyper focus on that heavily. Okay. Some other things to know is all the ways that you think about how we use air, think about it in terms of water. Okay? So what this could mean would be our CFM is equal to GPM. Not in a literal like for like, it's not 2000 CFM for every 2000 GPM. It's not a one for one. But the same symptoms you have with low airflow, you have with low water flow. Okay? A lot of our troubleshooting doesn't change the symptoms we expect to see. Now, something that I sometimes overlook this, or I don't specifically call it out, just because this is a simple way to think of this. What does get more complicated and what does change is the machine itself, is the control system. If you're not used to working on heavy equipment, we're talking large commercial RTUs as an example, then you may not be familiar with these controls that are in chiller systems. That's going to make it that you're going to have more struggle with the controls aspect of this than you probably will with this. But if you can get this in your head, you've just taken another step forward. Okay, coming back to the question, some basic things to know. Let's see. Ooh. A big thing that comes up is loop pressure. So, loop pressure. The way that I do this from a baseline perspective is we want to know what our loop height is, and then I like to add 8 to 10 psi to that to get us above our head weight pressure. So for every 2.31 feet of height, we have 1 psi. Okay, so if we had a 10-foot building and the equipment was, say, on the ground, say the chiller and the pumps were on the ground, there was equipment in the ceiling of the building, and so there's a 10-foot separation where we've got a total of 10 feet of vertical height, then that would make a loop pressure that I would expect at minimum pressure, okay, a minimum pressure of 23. Did I do that right? I didn't do that right. No, that'd be like 5. Oh, hell. I done got myself all screwed up. This is why I don't math. I've already started the example, so let's do it. All right, so 10, we're going to divide that by 2.31. Yeah, so 4.3 psi for a 10-foot tall and height loop, right? So then I would add probably about 10 psi to that. Now this is all going to be like on the suction pipe, for example. So then that would kind of turn into, I would just round to a 14 psi pressure target, right? There's a whole lot into that conversation. I have entire sections, like I have a whole section of a module over hydronics in my certification course at Chiller Academy. Covers this exact thing. Like I'm showing you this, I'm talking about the math, and there's a lot of variables that kind of play into this. Okay, this is a much more in-depth conversation. My point is, this is something that a lot struggle with. It's one of those huge sticking points where when I'm with apprentices, when you look at your water pipe, do you even have the pressure you'd expect to have? Well, what pressure should you start with? And it's not a default answer, right? It's not, okay, well, I should have at least 20 psi, 30 psi. There's no rules of thumbs here, okay? It's calculated based off of that specific loop and its design, its height. You could have one facility that's 10 feet, one facility that's 20 feet per floor. Like, those are things you have to think about. Now we do yeah, just these are things we have to think about. All right. My point being there, understanding your loop pressures is also going to help you get started. So I'm trying to take an approach to this question of how do I in a getting started. Okay, saturations, understanding water to air and the differences there or the lack of differences. It feels like it's a much bigger difference than it really is and from a service technician perspective. All of this is from a technician perspective. An engineer would probably blow his top if I tried to say these things are the same because they operate at very different parameters. But from a technician perspective, a lot of how we understand one can translate to the other. That's my point. Understanding your loop pressures and why they're there. If honestly, this one topic as to why we run certain loop pressures that we do, if you could get like up to speed on this, you've actually made a lot of progress into understanding loop systems and hydronics. If you can get comfortable with this one thing, you've made a lot of progress. So I do recommend, like, if you're gonna pick a handful of topics to really like prep yourself, that's definitely one of them. What else would I include? And if y'all actually have some suggestions on like, hey, he should study this or that, like, feel free to throw that into the comment. I'd be curious to see if y'all have any like what your suggestions might be to somebody in this position. Let's see, saturations, air to water, loop pressures. I mean, I guess I could say getting a really good understanding of control systems and electrical. That might be one to throw out there, but that's such a difficult one. It's an easy default answer that I see used a lot, but it's a difficult one to like really present to somebody because, okay, well, how do you do that? Sure, you could read more. The electrical is one of those. It can be really tough to try to teach. Like, okay, so maybe the schematics. There we go. Schematics. Even if you struggle with understanding electrical itself, get really familiar with just understanding how to read schematics. If you can do that, that will help compensate for whatever you struggle with on the electrical side in terms of like how to read, what you should be reading, things of that nature. So, um, yeah, learn. Now, there are some advanced schematics out there in the industry that we will use, but most of what the manufacturers are using are not like crazy out of this world advanced stuff. It is a lot of the fundamental principles of just basic schematics, the same schematics you would learn. Here, hang on. And this thing, I think they've got a different version of this now. This is what is this, 9th edition? I don't even know what edition they're on nowadays. But a lot of the stuff you would learn in terms of schematics, you're going to learn in a book like this. You know, this looks an awful lot like a Trane diagram. That's because it is. It's a type of ladder diagram. All right, so a book like this can help you get so far if you just want to have something to read. And this is something I got in trade school, right? This was a basic learning text we were required to have to even start classes. So that's my point. You don't have to. It's not as hard as it may sound to really learn this if you just take the time to learn it. Go find some schematics, and a great way to do that is just go find some IOMs. Okay, install operations and maintenance manuals. I can pull up a potential library here. Get this to work. Stupid Apple. Let's see. We'll go with this one and this one. Okay. So if we can scroll to some electrical schematics, it doesn't matter which ones you choose. I don't really care, to be frank. They've all got good information on some scale in there. Let's water schematic. Surely I didn't choose the one of the few of these manuals that doesn't have that. I sure did. Would you look at that? Come on, get your shit together. Okay, I know this one does. Okay, here we go. So this would be a blend of pictorial and ladder, right? And this is, I hate carrier schematics, to be frank, but if you can just take some time and just just pick one section, right? So, okay, so here's the main board, and I want to get familiar with these things. Okay, so just zoom in and just pick this one section and start looking into it, start studying it, and start finding out what these different pieces are. To be honest, if you don't know what something is, I hadn't thought about this till just now. I bet you could take a screenshot of these symbols and go throw it into one of these AI chats or something. Or actually, I think in Google search now, you can actually upload a photo, I think, or a screenshot, and Google will actually analyze it and then like feed you, hey, this is things that look kind of like what you showed me. I haven't done that. It just hit me that might be an effective way to try to figure out, like, what the hell is that thing? Like, what is that? Let me take a screenshot. Like, there's ways of doing this, is my point. Um, Learn this stuff. Like, if you can learn how to read this, like genuinely read this like a textbook, because at some point you'll have to be able to do this. This will eventually, as you scale and these systems become more and more complex, if you don't like seriously get your head around this, you're gonna hit a roadblock at some point. Okay, so don't let this be that roadblock. If you can learn this, even if you struggle understanding basic electrical principles, you're gonna be way further down the road. Order of operations, yes. Okay, so order of operations. Yes, okay. What I'm trying to think through is, okay, how do we present that? Because, while I guess a lot of machines are different, a lot of them are the same. Like the same basic fundamental, maybe slight tweaks to the process. Which that comes back to many times reading up on the manuals. And I saw your comment, by the way. Yeah, so does he. Haha. They learn what the chiller does when maintaining loaded and unloaded controls. Yeah. Oh, let's see. Loaded and unloaded control. I mean, I agree. These are core fundamentals. I'm trying to think of at what point, like, what's an actionable thing they can do with that other than just tell them to go read the manual, right? Which I know is on many ways the correct answer. Doesn't typically become it's not always an effective answer. Startup sequence, order of operations. Oh, GMP. Thank you, Michael. To your point, GPM, GPM, PM. Thank you, Michael. Um, I'm just, yeah. If you can, okay, here we go. Understanding lead lag control. So this is a topic I would want to research. If you can get your head around how lead lag works, that is going to scale into so much of what you need to understand. Just the core fundamental from a controls perspective. And then really getting your head around the startup sequence. And what you'll find, okay, with an RTU, I know with split systems on a thermostat, like once it turns on cooling, like fan, compressor, everything kicks on basically simultaneously. With an RTU though, what's the first step of that process when it gets a command to turn on? Um, it's going to be to establish airflow, right? Same thing on the chiller side. When we first get told to turn on, what's the first thing we need to establish? Water flow. So even from just an RTU perspective, if you can really get your head around RTU staging, like startup specifically, if you can get your head around the startup process, then you can start. You'll have a lot to then bridge over into how chillers work. And right, fan proving, right? So fan proving safety is also going to be the same thing as a flow switch. So like those things are fully interchangeable in terms of concepts. They work different. One does air, one does water, but the concept of what is happening and why we need, because we won't start compressors until we prove fan on a commercial RTU. Period. Right? So now if you're not working on that equipment, that may not be as helpful to you, but if you have at least gotten into some of that equipment, those are going to be basic um, like startup procedures that fully translate. I think this is a pretty good breakdown of like a really good if you can if you're just new to chillers and you want topics to research and get your head around and things to just spend some time thinking about. If you can do this, you're well on your way. And again, I all of these are things that I completely go over in the certification course. Okay, not to make this a sales pitch, I'm just saying, like, if you really want to dive into these topics, get a better understanding of it, and if you want to take this seriously and really work your way into being a serious chiller technician or working on chillers, that course is built with all of this plus everything else you need in mind. Okay, so you can research each of these things independently. You can come up to your own conclusions. Something I will warn you warn you on a lot of these topics. When you're researching this stuff, keep in mind that many times the answers that are being given through a blog or article, whatever the heck it is you're reading, they're usually taken from a either highly general approach or from an engineering perspective where they're writing to other engineers they expect to read this, not as a technician. And there is a difference. The way we apply and need to think about these things from a service perspective isn't exactly the same thing as how engineers or just general applications need to apply them. Like we do things in a slightly different way, and it's just enough that if you're not careful, it'll confuse you because it may say some things that could mislead you, and I'm guilty of this myself. It can mislead you and cause a lot of confusion as you're trying to figure these things out. So if you're going to self-research on these topics, be careful of the context of what they're talking about when they're describing this stuff to you. You'd be shocked how much of these things overlap across the board on many different industries. So they could be talking about oil and gas applications. They could be talking about power plant applications. They could be talking about a lot of different stuff. There's still good information in there if you know how to use it, right? So that's my caution. Like if you're going to do this on your own, you don't want to go through the certification course. It doesn't hurt my feelings. It's fine. Just be aware of that, please. And on the Michael, on the approach, so that's something that as they get into the saturations topic as a whole, those are some things I expect to come out of that, right? So that's something they can work into as they really start working into saturations, because technically approach is still something we can and could and some of us do use on the air side with the DX on RTUs or whatever. You can use those same, they're different values, but we have approach on coils. Now, I'm not talking about what Linux did with their approach back in some of their splits, but like just your leaving air temp to coil temp, right? That approach is useful, is very useful, just like it is with a chiller or hydronic system. It is a very useful value to understand how well is this heat exchanger performing at these given conditions. Anyway, and then the efficiency of the heat exchanger, like the SEER rating and all that stuff, starts to play into that, and da 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 da. We go down a whole rabbit trail there, but yeah, really good to see everybody. Thank you for joining. Always enjoy just coming to get to hang out with everybody every Monday. I guess this is a huge fun part of my week. It's Hanukkah time for us. Really excited about that. Kids always love getting into it. So we're doing it the whole week. And for the first responders out there, wear your stuff proud, guys. Thank you for your service. Thank you for your work. You do really incredible things that most people won't ever notice, and that's okay. All right. YK high oil temp troubleshooting. Ha ha ha. Okay. So, coming from Mr. Michael himself. Pull this in. Okay, so high oil temperature on a YK. On the YK, we have a oil cooler built in. There's a few things that we need to really pay attention to here. So I guess I could. Do I want to draw this? I think I should draw. Oh, here, actually, I've got a really good schematic we can pull up and look at. So let me go to my image here. Let me pull this. Scroll down to what I want. Right here. Okay. Yep. So this is a YK compressor. This is the basic oil cycle that we're going to go through. And we've got high oil temperature that we need to troubleshoot. So there's a few things that I want to look at. One, it's going to be the actual, actually, before we get into that, temperature sensor itself. I want to verify my oil temp sensor. So there is, it depends. This one shows it on the back. A lot of them, it's going to be up here on the front plate where the pump is at. You'll have your temp sensor there where we can actually monitor sump temperature. Okay. So I do want to keep track of that. And one, just verify, is that even correct? One of the ways you can do that is taking a line temperature leaving the pump. Okay. So if we're concerned that maybe that temp sensor is not reading correctly, I can compare that to my leaving sensor coming out of the pump, or the line, the oil discharge line coming out and going into the oil cooler. Another way to do that would try to be maybe getting a surface temperature down lower on the sump. So not as big of a fan of that, but that is possible. You can get your temperature down here on the shell housing. Now this is not insulated, so, and keep in mind it's not going to be perfect. That's part of the tricky part to taking these measurements. They're not going to be perfect to the actual thermistor, but we're trying to see, are they even in the same ballpark in the first place? So that's one of the first things I'd want to do is my temp sensor even working correctly? Another one I'd want to do is the oil heater actually turning off? So uh, the older the older systems have a thermostat on the back of the oil heater. It's supposed to be set for 180 degrees. And then the control panel also controls a relay on the I/O module underneath the microboard that triggers this. So there's actually two layers of temperature control you're supposed to have. So one is the I/O module engaging the oil heater, and it's through that relay, which is, it should be, I think, the K1 relay if I'm not mistaken. I'm pulling off a memory there, so I'd have to look that up to verify it. But off of the I/O module, you've got a oil heater relay. Are you pulling amps while the machine is online? So this heater should not be working while the machine is online. If I see amp draws while the compressor is running, I know I've got an issue, and I need to figure out, okay, more than likely that K1 relay has failed. Now, typically they fail open in my experience. They don't usually fail closed, but at any point, like, it could have an issue. Is that temp sensor in a dry well? I don't remember. Let's see. Is that in a dry? I don't think so. No, if memory serves, I think the temp sensor is in a wet well, meaning it is making contact with the refrigerant or with the oil. I think. I don't actually remember offhand, because they do put some temp sensors in dry wells and other locations. I would have to just look at it. I don't remember straight off of memory. I could probably pull a picture and look, because I've got some where I can see the front of the sump. Let me see if I can find one of those quickly. Let's see. It may depend on the size of the machine too. So here's one. Let's go Control F. Let's see, is that? There's the transducer, drain. That's for our pump. This is our discharge line. Yeah, this temp sensor should be, I think, maybe this one, this is a larger series, by the way, right? So this isn't a smaller one. This one may be on the back side, so we can't see it. I think the smaller ones are up in the front. The larger ones are in the back, something like that. It's been in... Anyway, I don't remember. That's something we'd have to just look at and try to verify which is which. Either way, if it is in a dry well, all right. So if it is in a dry well, then yeah, that would be really easy. You can just pull the sensor out. My memory says it's not. My memory says that the sensor is in a wet well, but I could be wrong. So you could verify that for yourself. Anyway, so yeah, is the heater, and it could be more than just... So something to keep in mind, if this heater is set correctly at 180 degrees, then during operation, your oil sump is going to be low enough to allow it to keep functioning, because this heater is there just as a kind of like a safety, if you will, the thermostat in the heater. So it's only going to actually function when the oil starts to basically overheat in an off cycle or something, because that's the only time this heater is engaged. It's when the chiller is shut off, or the compressor is. Temp creeps up during high load, but calms back down once we're maintaining load again. One of the things, okay, so moving beyond the heater and the temp sensor itself, our oil level, like the volume of oil, will have an impact. The lower volume will cause higher temperatures because that oil is moving through the system faster and getting less processing time. So because the flow rate of the oil is increased due to lower volumes, it's not spending as much time in the sump, just kind of naturally cooling. That will have an impact. Even if it is going through the oil cooler will compensate. It does adjust, and I'll talk about that in a second. But we want to make sure we have enough level. And if you're down into the minimums, that especially at a high load like you mentioned, the that will increase your operating oil temperatures, right, as a whole. So the one you have is 1,050 tons, sensors in the front. Doesn't look like any, yeah. And remember, the key thing to a dry well is going to be, does it have like that plastic cap whip to it? Let me see how I can explain this. I don't have one here at my desk to show. I need to pull one of those out of my storage. Does it have like the little a plastic thread piece, or does it look like a compression fitting, right? If it's full compression, or actually some of those I think are the big, they're actually a plug, if you will, that has the temp sensor mounted inside of it, like you see on the air cooled machines. Those oil temp sensors are basically just a brass plug that has the temp sensor inserted into it, and part of it's like a single mold. So if it's any of those kind of styles, yeah, those are wet well sensors, not going to work. The only ones that'll come out is if it's got like the plastic like flex whip on where the sensor threads into the well itself. If you see that, like you see on like a Trane water temp sensors, that's immediate indication that you can change it. Well, actually, the water temp sensors on the Yorks, those have those same plastic like flex tips to them to help kind of take some of the strain out of the wire flexing. So that's a dry well. Just as a reminder. Heater is turning off. Check contactor in the VSOP panel to make sure it agrees with the OptiView relay output. Yep. Sensors in the front, doesn't look like 180 degrees is the trip point. Right. Oil level is about 85% glass. Okay, so getting back to, we have to make sure we have enough oil. That's the next thing. 85% of the sight glass, I'm happy with that. That should be enough. And I'm assuming yours is the style where you've got the full front face glass. You don't have just the two glasses like what I showed here, right? So with this one, we literally just have the two glasses there, right here. Whereas some of the designs, we've actually got we can see the full column in between those glasses. So either way, 85%, that should be enough oil, so we can eliminate that, right? We haven't eliminated the sensor necessarily, but we have eliminated the oil heater and the level, so we know those are functioning. Then we come into our oil heater itself. Is the oil heater functioning correctly? One of the ways I'm looking at that is, okay, so we've got our metering valve coming in. So if we come back to this photo, we can see that right here. So this is our oil cooler. This is the metering valve. This valve is going to have a sensor on the leaving side. Actually, hang on. That is our oil pressure regulating valve, right? Let me follow this here. That's our vent line leaving. Okay, so this is a constant speed oil pump. That's our oil pressure regulator. That's our suction. So you can't see. Let's see. I'm trying to get my head straight here. You cannot see the coming down. And this should, like down over here, take off and go up. And this is our liquid drop leg coming out. That will feed into the metering valve, and then that comes back off into the evaporator on this backside here. Either way, without getting into the weeds here, the metering valve has a sensing line on the oil temp leaving. So basically, as the oil temp increases, the valve should be opening, and then as the valve opens, more cooling is put to the oil, and it slows down, which you can see right here, right? So this is our oil entering line. We have our oil leaving line. There is a sensing bulb here, and then this is controlling how much flow goes through the cooler, and then this goes back to the evaporator. So this is coming off of our liquid drop leg coming out of the condenser. So your refrigerant charge level or refrigerant level control period does have an impact on this. So are we feeding a consistent and subcooled refrigerant to this metering valve? If we're not, that may be affecting, especially at high loads, how much refrigerant we're actually feeding to the oil cooler. So if we're not feeding enough refrigerant to the oil cooler, that could be why we're seeing these temperatures increase, which at that point, what you're going to see is you're seeing the temperature as it returns back into the sump increasing. So that when we say their temperature is increasing, we're seeing the sump temperature increase specifically, which means that it's already made its way all the way back around. And this should be basically, well, I guess not our coolest point, but it's our return point coming back out of the compressor. So just bear that in mind with this particular system. And if we have subcooling and we have good liquid level, which on these machines, 1/3 to 1/2 sight glass is kind of like a starting point, and then you can tune it in from there based off of your subcooler plate level. So that's one of the things we have to look at. It's a whole nother in-depth conversation. Point is, we need to make sure we're feeding enough liquid or a subcooled liquid to the oil cooler metering valve, and that this valve is actually like functioning properly. So one way to tell that is just, is it actually opening? You can check your leaving temperature line to see like what that looks, because this will feed just back into the evaporator shell. It just has a port where the suction gas or the flash gas, whatever's coming out of the oil cooler, is just returning back to the evaporator. So you can take a measurement of that. Is this heat exchanger even just functioning? Are we feeding enough refrigerant into it? That could be the next issue itself. Maybe even if you're feeding proper subcooled liquid to it, doesn't mean that it's actually opening and controlling properly, which again, at high loads, when we need it to open, if it's stuck at a more closed position, then it may work perfectly fine at lower loads. But as you see your load increases, this metering valve may not be keeping up. It may be stuck or not. It's just not working correctly. And the thing is, keep in mind, if this valve was to, we're not monitoring suction superheat coming off of this, because this is just feeding back into the evaporator on these machines, which it's not like a regular refrigerant circuit. We were worried about flooding. Like that's not a concern here. We're just going to dump, even if we do have liquid refrigerant leaving this heat exchanger, it's just going back into the evaporator, which has standing liquid in it. Like, it's not a concern. So, just things to think about in how you're going to troubleshoot the refrigerant circuit on this. Now, in the case that all of this checks out, temp sensor's good, oil level, heater, and the cooler all seem to be functioning, then we get into our worst case scenario of there may be just something mechanically wrong. So keep in mind, our oil is what is cooling all of these components up here. So this is our pinion and bowl gear. This is how we're transmitting or transitioning from a low speed to a high speed shaft. Like, all of this is cooled by the oil. So if everything here is functioning, but we start running elevated oil temperatures, then that means we have some kind of mechanical stress happening up here. Something is going on inside of this assembly that is causing us to elevate oil temperatures in the wrong way. And that becomes our next point of concern of, okay, what up here is generating that extra heat? If everything else is working, what up here is causing that? Now, like I said, that's where you get into your worst case scenarios. Most of the time, that's not going to be the scenario. And most of the time, if you're really having some severe issues up here mechanically causing heat, you're going to see that in your oil samples and metal shavings and those kind of symptoms first, in my experience, before you'll ever actually see this generate so much heat that it causes the oil temperature to rise significantly in the degree that's been explained so far. So, yeah, so that's the approach I would have. And if I haven't caught, like, say, metal flakes in the oil sample, or if I haven't taken oil samples recently and I'm seeing these conditions and I've verified everything else. Okay, I had a brief blip there. That's an internet issue. I apologize. Okay, and just to make sure everything came through. So if I have a situation where, like, I do think that my heat is coming from up here and I haven't done an oil sample recently, then that's what I want to do. I want to take that sample and have it analyzed for metal particulate in it. You know, where's my zinc, where's my aluminum, like, what are these levels at? That way, if there's an actual problem up here that's going to cause heat like that from friction, we're going to see it in the metal analysis specifically. I need to know what that is, because something is just gone wrong, just plain on. So anyway, that's the worst case scenario. Every troubleshoot like that I've had, it was somewhere in here. It was either a sensor, it was something weird with the heater going on, or the oil cooler itself was just not functioning correctly for the variety of reasons I described. Let's see. So you had some other commentary. Running normal conditions, set point. Little more info. Condensing water temps got high due to tower fans not controlling properly. Okay. So I don't think so. Then the part of that question would then be: does the condenser water increasing in temperature have an impact on the oil temperature? Well, it's going to increase our head pressure. It's going to increase our condenser pressure, obviously. So the only reason I would think that would affect our oil temperature is if it's causing us issues maintaining subcooling. Because if we start having subcooling and liquid level issues in the condenser, that's going to impact the oil cooler metering device. Because keep in mind, YKs do need subcooling, especially when loaded, to operate properly and efficiently. It's not like these other machines where they have economizers and stuff to make up for it. So they're not trying to achieve subcooling. They're just trying to get to a full liquid state. With a YK, we have a dedicated subcooler circuit. We need that machine to have subcooling in order to function, not only at the evaporator and the metering device correctly, but also at our at our oil cooler metering valve. So it's possible that you may have enough flow that you're satisfying the um, evaporator. You're not running into suction limiting and stuff, but yet you're not giving the oil cooler enough subcooled refrigerant at load to feed enough through that cooler, right? So that if it came down to if it came down to the like condenser problem, that's the only way I could think of in the moment how high condenser water might affect it. It comes back to just what kind of subcooling can we achieve. All right, so you weren't there, but what is typical subcooling value to look for? Yeah, so fully loaded and everything set correctly, like all your liquid level on the condenser set correctly, you should be able to run what 8 to 12 degrees of subcooling, and like so that's the subcooling target we should be trying to hit. And when the machine is unloaded, that it's common to see that get down into say 4 to 8 degrees, somewhere in there, kind of float in that range. That's very, very normal when derated at an unloaded state. And then as the machine loads up, you should see that subcooling increase. This goes back to some of our saturations talk and stuff we had earlier as to why that subcooling would go up or down. It's a separate conversation. But yeah, that's going to come back to your load. So if you're only seeing 4 or 6 degrees at load, like when you've truly got this machine loaded and you're running close to design TD, temperature difference, across the evaporator and everything like really stacked up, and you're only seeing 4 or 6, I have questions. Like, okay, why are we still that low? Those are derated part load numbers, not loaded numbers. We need to resolve that, which plays back into, okay, are we feeding enough to that metering valve for the oil cooler? All of that plays into the same conversation. Um, I am curious. Well, we can move on. Anyway, hopefully that gives you enough to go off of to where y'all can kind of troubleshoot from there. You've already done some of it. There's just a little bit extra, especially that oil cooler being the primary. But before, like for me, that's why I bring up the other stuff. It's really easy to test that heater. It's really easy to test the temp sensor comparatively. Um, and it's much easier to test or to just look at the oil level. Those are really easy checks to do that take a couple of minutes. That's why I start there, and that's why I push that out first. Is okay, let's get that resolved. And if those are good, then we can take the time to dive into the oil cooler as my next kind of final step, if you will. And where's the oil cooler at and its metering valve and all that stuff. Because that starts to it takes more time, gets more complex. And if you spend all this time trying to troubleshoot the oil cooler first and it's really just an oil temperature sensor issue and you never went and verified that, or something happened and your oil heater is just constantly on all the time, then like you miss the really easy thing to go for the hard thing, right? So that's why I want to start with the other stuff first, get all that resolved, then put time into that oil cooler. That's my personal like troubleshooting process there. Okay, let me catch up on some of the chat here. It One of these days we'll figure out this whole language thing. There, is it Wallen, or I'm not sure how to pronounce your name, or at least the screen name, but we'll figure out this language thing one day. We'll get there. How does oil enter the evaporator? Yeah, okay. That's a good chat. We'll circle back to the oil in the RTAC in a second. We just kind of catch up here. Michael been blowing it up the whole stream. just just playing. The chiller is running normal. Okay, so we got another question there. What question is usually asked in an interview? That's a good question. Motor sounds fully. If YK chiller oil return is not working properly, what is possible reasons? We'll get into that. That's going to come back to the eductor circuit. There's several things to discuss there. Then snow on rooftops. Yeah. Well, we're actually cold today, and we've been cold for what, 2 weeks now. Sterling called. He pulled out the hoe Frylock. I see. How you doing, Sterling? You're welcome, bud. Good one. He threw some trash at me earlier, so he earned that one. You may not have actually meant to hit O, or maybe you did. I don't know, but he earned it. It's good to see everybody. Doesn't subcool decrease with load increasing? It depends on the application. When we're discussing it from a chiller application, no, subcool will increase as load increases. There's a really short answer to that. Yeah. So since we stack less refrigerant, that we expect to see higher subcool values when loaded. I figured, Sterling. That was a good one, though. I still got him back. Okay. Let's get into our next question up here. So how... Bear with me. Let me get this set up so everybody else can see. Oop, wrong one. Get my buttons right. And if the stream looks or sounds slightly different today, I got a new computer and I'm still kind of getting some of the bugs worked out, but we're kind of rolling with it. All right. How does oil enter the evaporator and return to the compressor in an RTAC chiller? And what prevents refrigerant from flowing through the bottom return line? Okay, let me actually just pull up the manual to this, and we'll actually look at the RTAC's refrigerant schematic they have. CGAM, let me get the RTAC pulled up here. CGAM, nope. RTAA, HD, where are you at? This one? Nope, not that one. Here we go. Yeah, RTAC. Okay. Let's switch over to the overhead. And we'll pull this out. Let's get down here to the schematic. I think we passed it right there. Nope, not that one. Okay. Let me just zoom in here. Yeah, I'm going to get more of these set up on the computer. I don't have to do it this way. But okay, so looking at RTAC, so this is your basic refrigerant circuit. So here's our compressor. We come out the discharge into an oil separator. Okay, so from the oil separator, we have discharge gas comes out, makes its way back to the back to the evaporator, and then at the bottom of the oil separator we have our oil temperature, or I'm sorry, our oil return line that comes back and feeds into our compressor oil filter, which all this is internal. And then the oil cycles through. So the motor and the bearings on these compressors are on the low side of the refrigerant circuit, the low pressure side, and the oil feed itself is on the high pressure side. And that's how we're able to maintain oil flow with no pump on these machines. So we're using differential pressure to go from one side to the other for flow specifically. Now the question is, how does oil enter the evaporator and then return to the compressor? So what we have is, it should be 30, right? Yeah. What we have is these oil separators don't remove all of the oil from the refrigerant vapor. Okay, it removes a lot of it, but not all of it. It is not a pure oil, or I'm sorry, a pure refrigerant that leaves this and heads back to the condenser to recirculate. So the little bit of oil that does make it up into this does process through the condenser, and then as it goes through the condenser, it does drain back out and start back through our liquid line. Okay, same way, just oil flows through any refrigerant circuit. Okay, whether we have a separator or not, some oil does make it up into the condenser, and we do have that drain back into our evaporator. Now keep in mind, these evaporators are falling film evaporators. Okay, so bear that in mind with an RTAC. So if we zoom in a bit here, we're going to come out of the condenser liquid line, and then we come over to our EXV, which feeds into our top spray rail of the evaporator. Now, as we feed into this refrigerant is controlled by a liquid level sensor. Okay, so it's monitoring and just maintaining just a couple of inches of liquid in the bottom of the evaporator. And what happens is, because this is a falling film, notice that our suction line is on the top of the evaporator here. So in this evaporator, water is inside the tubes, refrigerant is on the shell side, and our metering device feeds into the top of the evaporator, and our suction feeds off the top of the evaporator. Okay, so both connect to the top. This allows, as refrigerant boils off, this allows the refrigerant to come out into our suction line as a vapor, but what doesn't come with that vapor refrigerant typically, because we're liquid refrigerant here, high pressure liquid, low pressure mixed refrigerant, so liquid vapor mixture feeding into the evap. Well, we're just vapor coming off of here, and what gets left behind is the little bit of oil that is in here goes with it, or I'm sorry, it stays. So the little bit of oil ends up staying here. We have to do something about that, because that oil will float on top of our refrigerant. It affects our heat exchange. Eventually it will oil log the evaporator to where it won't allow us to return oil at all. And or I'm sorry, it will oil log the evaporator, which will prevent us from exchanging heat, is what I meant to say. We'll start having superheat issues, oil level control issues. All that will begin to start when we start having oil stack in the evaporator. Causes a lot of issues for us. So we need to do something about that oil. Well, that's where we have this return line off the bottom of the evaporator on these. And it can be on the bottom because that is where the liquid refrigerant is. Okay? These machines maintain a very low liquid refrigerant level, and when the machine is running, which is when our oil recovery circuit or oil return circuit, as this manual will describe it as, oil return, that only works while the machine is running. So our oil return circuit doesn't do anything when the machine is off, or when the compressor is off. Anyway, so in that case, all of the liquid refrigerant in the bottom of the evaporator is mixed with heavy oil to refrigerant mixture. So even though oil stacks on top of the refrigerant, It only perfectly separates when the refrigerant is not boiling off, when there's no flow happening. When there is refrigerant boiling because it is in operation, the top several inches of that liquid refrigerant will be oil liquid refrigerant mixture. This is also true on larger machines that run higher liquid levels. That they run up to half of the barrel could be liquid refrigerant. So on those machines, those are also included. The top several inches are a mixture, even though oil floats. Okay. So because of that, we can draw that oil off into our return line. And this is using a, let's see, this particular one I don't think uses an actual eductor. This one, it has, I believe it has a port in here that is metering that. So it's not literally drawing liquid refrigerant and just dumping it straight into the compressor on this particular machine, because a lot of machines use actual eductors. If memory serves, this machine is not using an eductor like a lot of machines do. This machine it draws that liquid oil vapor off. I'm sorry, that refrigerant oil mixture off of the evaporator and then sends it through like a fixed orifice, if I'm not mistaken, into the compressor return and that flashes off the liquid refrigerant, oil stays oil, and that's how we're able to get that oil back. And we process through a oil filter. Okay, no, and it's not an oil. It's actually I'm sorry, I called it an oil filter. It is a dryer. It is just an oil line dryer, but it's just a regular dryer you would have. There's nothing special about it. It's just a filter dryer, and it's there to process water that might get introduced at any point, right? So if we have water, some minor acids, things of that nature, that's what that filter dryer is there to capture. That's his purpose. So the other part of your question was, okay, so how does it enter the evaporator and return to the compressor? Okay, we talked about that. And then what prevents the refrigerant from flowing through the bottom return line? Well, one, this service valve here can fail. And if somebody closed it at some point and didn't open it again, or if it's not open, you have to pay attention to where this line is at. I would have to verify by reading a little more. I don't remember, because a lot of these machines, you have to calibrate this valve yourself in the field. These valves aren't made to go full open. They may only be, say, like 1 or 2 turns open, or and that's how you're able to set flow. So if you open this too much, it could overfeed into the compressor and cause an actual flooding. That's something to be aware of. I don't remember if these RTACs require that or not. I know that like a Trane CVH, their big centrifugals, you are required to do that in the field manually. Anyway, this valve could be one issue. Another issue could be this dryer. If this dryer has gotten plugged up and it's just not allowing flow back through it, that's going to also cause the oil to begin to stack in the evaporator in the wrong way. So that would be something else I'd want to pay attention to, is, okay, is it a dryer issue? Is this valve having an issue? Let's see. I mean, it's possible you could have debris. Like if you had some kind of debris get into the system to where it plugged up, it probably wouldn't make it to the compressor, but maybe over here in this area at the evaporator, where just, I don't know, a flake of, maybe somebody used some 515 or something on a sensor, and they've now got this big chunk of dried up 515 blocking the port. Like crazy ridiculous stuff like that can happen. Does happen. Something, you could just have some kind of debris maybe get in the way. I'd say it's far less likely. It's far more likely, in my opinion, that this dryer or this valve are going to be your primary issue, and that's going to be preventing you from flowing back into the compressor. Those are the main areas I would want to be paying attention to. If I thought or if I knew that I was having an oil return issue causing it to stack in the evaporator. Let's see. One of the ways to know is just pay attention to your approach value. So if your approach is really high, but you're confident you have proper liquid refrigerant charge and your tubes and flow, like your heat exchanger is working correctly, but yet you still have high approach values, which on this machine should be like, what, 3 degrees. So approach is the difference between saturation and leaving water temperature. So the difference there, if it gets to say 3 or 4 degrees or above that at load, that's when we start having to ask questions, and it could be an oil issue. I think these machines did use, or at least some of them did use, the original level sensor design. The original level sensor with an actual like float magnet in there does get affected by the oil. That oil will cause it to float up, and it will read a higher level than is actually there. In that case, that'll actually end up starving your evaporator. In order to fix that, we've got to get the machine to feed enough liquid refrigerant in there to start trying to get some of that oil back out. That is one of the major problems that Trane has had with their original float designs, is that oil, as it begins to get foamed up as the evaporator is running, will cause a lot of issues with that level reading really high, which will cause your metering valve to pinch off, and it just won't control correctly. And it's a pain in the butt to try to work around. So whether you try to fool the sensor to increase the liquid level enough to start getting some of that oil to return, like we just have to try to do something to keep the machine online and get that oil back. Like that becomes kind of the tricky part, because part of what will happen is it'll read high level, it'll start to starve the evaporator, that'll turn into suction limiting if it doesn't just go into full-on suction pressure trip. Like a whole series of that oil in the evaporator could cause several reactions that are shown as symptoms in other ways, like suction pressure limiting being one of them, because it is starving the evaporator. Not even a heat exchange issue. Basically what that'll look like is you'll see a normal or a high liquid level position, but yet you're running suction limiting, and you've got really high suction superheat coming back into the compressor. When you see those conditions, but yet your level sensor says it's normal, or it's high and it needs to feed less, that's obvious sign, okay, probably oil in this case. We've got to do, part of the goal is get the machine to just stay online long enough to get that oil out. Because eventually, if we can let it run at a minimum state, get that oil back out of the evaporator, that will start to correct itself. But we have to have operation and runtime in order to make that possible in the first place. So, yeah, I mean, worst case scenario, yeah, you can see where it notates. It has a service valve on the bottom of the evaporator where you can recover from. If you really had to, something you could do is try to, say, recover that oil with a recovery machine back into, like, over here on the high side of the system or something. I'm really not a fan of that, but let's say you were in really worst case scenario. The trouble is, whatever liquid refrigerant, like, you don't really want that liquid refrigerant over here. Like, you really, really don't want it over there. But there's just, again, if we were in a really worst case scenario, because I'd hate to trash this just because of that migration. So the idea would be, okay, well then let's just move it back over to the high side. We'll have to mitigate managing that. Here's the problem. If we truly put it in the separator, and this is where it just gets really tricky, okay, there's not always a perfect answer. That if we put that refrigerant and we start stacking liquid refrigerant in our separator, that liquid refrigerant will then stack in the bottom of our separator and it'll sink below the oil. So then when we go to turn the compressor on, what are we feeding? Not oil. We're feeding refrigerant right back into our compressor, right? Same issues we have with any circuit. If bearings don't need refrigerant, they need oil. Anyway, it's just something to be aware of. We're talking like worst case scenarios. Best case scenario, get the machine running, keep it online, oil returns, you go back to normal. That's the target we want to try to hit. Let's see. Do we need to cover anything else on that? No, we should be good. Okay. Yep. I think that summarizes that pretty well. All right. You don't get it. I thought in full load, more refrigerant collects and less gets stacked in the condenser, therefore subcooling decreases. So Sterling, you're getting confused. You're getting confused by how do I approach this? If you're talking an RTU and no, because that's not even true. Technically what happens, Sterling, is if the system is charged and controlled properly, we don't actually end up moving less through the condenser. If anything, we may run slightly higher condenser liquid levels, at least in like the equipment we're discussing. We end up running slightly higher levels. And that higher head pressure due to more load and higher levels ends up creating a higher subcooled environment because we're getting that liquid refrigerant. Well, it's we end up stacking higher in the process. Like that is what's happening. Now there are cases where I've seen, like when I'm working on split systems, you had to be careful when you were charging at a low ambient, low load condition versus a high load on the coil or on the condenser, because well, hang on, no, that's not right. Yeah, so you see part of the issue here. I'm going back to the days of working on splits, and like there was a big difference. If you charged to one time of the year compared to the other time of the year, that's what it was. Yeah, so even with a split system, this is where this concept first rooted for me. If I was at peak summer charging a split system and I had a full load on the evaporator, I would intentionally overcharge just a little bit. So if I was targeting a 12-degree subcooling and I was in like triple digits that day, the evaporator had a 20 to 25 plus degree load across it, right? Um, and I'm talking about return to supply temperature on the air side. Then like I would shoot high because I expected to run a higher subcooling at that high load. And then as the load reduced, as ambient temperatures dropped, I knew my subcooling would also drop. And I didn't want to have a case where then if I got into a low, or if I got into, say, normal operating conditions where I was, say, between 80 to 100 degrees and a normal evaporator load of 15 to 20, right? So if I got into those conditions where I had less load, I knew my subcooling would drop. And if I didn't overcharge just a little bit, I would end up looking like an undercharge once my load decreased. And so that 15 degrees at peak max load would then turn into 6 or 8 degrees of subcooling. We're talking about our standard split system with a TXV. So as load increased, as head pressures increased, it does end up like you do end up in it's more than just the physical how much liquid you have. Okay, so it's not quite as simple as just liquid level increases or decreases. Um, it also comes back into what is my condenser head pressure compared to ambient, and how much cooling is that heat exchanger actually achieving on the refrigerant that's in there, because you could maintain the same physical liquid level, but yet if the heat exchanger becomes less efficient, even though the liquid level doesn't change, your subcooling can drop because of that, right? Versus if you had a really efficient heat exchanger, and so it went from dirty to clean, we could say it in that context. You could go from very little subcooling to a lot of subcooling, right? So this is challenging because there are, and I see this with trainers and teachers in the industry. We get very we teach one aspect of the dynamic when there's actually like three or four aspects that play into that value, and we think of it in terms of liquid level is actually changing position many times, when in my experience, once the charge is in the machine and set, once your levels are set at operation, the levels don't really change all that much, because what increases is the rate of flow. Okay, the rate of flow increases, but the actual levels don't really increase as much. Around the concept, I guess I need to go. Yeah, it's okay. I heard they came up with new gen for the liquid level sensor that supposedly doesn't get tracked. Yes, yes, the Trane does have a newer generation. It's no longer a mechanical magnetic float. It is just a sensor that is reading continuity of the oil to refrigerant, and refrigerant has a different continuity or resistance to it than oil does, and so um, it's the sensor can then actually calibrate itself and determine, okay, this is refrigerant, this is oil. So even when there is foaming of the oil, it doesn't fool the sensor as easily. It still can, but it doesn't fool it as easily, and it's able to still see the actual refrigerant level, even though there's a column of oil foam on top of that refrigerant, which has previously would have caused our float to increase and given us a false reading. Because in an air cooled, at least, it makes sense that subcool decreases with high load, but maybe with flooded it's different. Well, but I haven't seen that, so I'll use an example. And I'm sorry, I will get to the other questions. I'm getting hyper fixated here. Um, when I'm going to use a York YCAV as an example. When I'm working on those, the if I've got a minimal load and I'm running like really unloaded, I may only be doing 8 or 10 degrees of subcooling coming out of my condenser. Proper charge, the machine is in proper condition all the way around, right? But just taking an operation check with it unloaded, and so say I've only got 5 or 6 degrees of TD across the evaporator, compressors running at, I don't know, 60% RLA. That circuit is producing 8 to 10 degrees of subcooling, somewhere in that ballpark, which for a lot of machines would sound really good. Well, those machines actually run higher subcooling than what I see other machines run. York, I don't think gives us, or at least in the literature I have, York doesn't spell out the subcooling on those machines. But just from taking readings on them thousands of times over the years, I noticed that when they're actually at full load and they're maxed out, they're pushing 20 something degrees of subcooling. That's an air cooled screw with a DX evaporator. Okay, so the refrigerant is in the tubes water's on the shell, and at load, I'm at 20, 25 degrees of subcooling. When I'm unloaded, I'm at like 8 or 10. Now, this is for proper charge. Now, here's something I'll throw. Okay, this just clicked. Maybe this is causing some of the confusion. I don't know. You can tell me. Where this gets screwy is if you're charged correctly. So if you're undercharged and you're not maintaining proper refrigerant levels because you don't have enough refrigerant in the first place to maintain those levels, then you'll see what you're seeing. You'll see your subcooling drop. You'll see lower levels in the lower liquid levels in the condenser because of charge. So maybe this is the confusion here, because machines that I see do that are due to charge issues. When they are properly charged and they've got enough liquid refrigerant in there, I expect to see higher subcooled values as load increases, because my head pressure increases. Like, these things are all correlated to each other. And then as my load comes back down, I expect to see my subcooling fall with it. Subcool is tied to load. You are correct in that. I agree. We're in agreement there. Subcool does fluctuate with load. But a properly charged machine, I expect to see my subcool increase compared to unloaded. Whereas a only partially charged, because the same thing is true. The same thing is true for, let's go with a water or an air-cooled scroll machine, okay, a CGAM. You've got two compressors on the circuit. This is also true to an RTU. If only one compressor is online, many times you may only have a couple of degrees of subcooling with only one compressor on running a partial load. You get that load increased, get both compressors running together, load that circuit up, and then all of a sudden you look like you've got really good subcooling. That's another example. Proper charge, more load, in a scroll compressor case, more compressors, higher subcooling. We also see this with VRF. If with VRF machines, as load increases, as compressors spin up, as we need to process more BTUs, we see our subcooling track with that. Subcooling increases as our load increases on the machine. Is that for water cooled only? No, this what I'm saying is across the board. Yeah, I'm saying, like, I'm taking an air cooled approach to this. I know, like, this is fundamental. This gets back into why saturations are what the saturations are. But with a CGAM, it doesn't get screwy. You only get screw. Okay, all right. Good one. Good one. Is that helping? Like, am I helping or am I just making it worse? Genuinely, like, because that would be my challenge. Like, machines that you're seeing subcool fall when it's at full load compared to unloaded, I would challenge the refrigerant charge of that machine. And I would go as far to challenge if that charge is accurate. I mean, is this helping? Part of what makes this more complicated is because we are dealing with more complex refrigerant circuits where more things are happening, and we have derating ability. Like, those add a lot of variables. Yeah, and I'll tell you, like, what you learned is what is very much like how I remember learning it early on. The reason I decided to get deeper and change my position on this was because what I was taught and what I actually saw when I took data analysis didn't line up. Like I remember learning, I don't remember exactly how it was explained, but I remember having a concept early on and where if like what you said, the subcooling is going to track with the load and stuff. It was something along those lines. And then I remember getting super confused when I would walk up to machines and um and I saw the exact opposite basically um of what is expected, right? Of instead of more load meaning less subcooling, I saw more subcooling with more load. That's what it was. I remember it just clicked. I remember the day this finally clicked in my head. I remember it vividly. So keep in mind, I got into trade school a I was what 2 years in. I got into trade school my third year into the industry. I so in my fourth year, which was my second year of school, because I went through a 2 year program, we had a commercial refrigeration class. We actually had walk-in boxes in a lab that we could turn on and like practice with and charge and recover from and all this stuff. And I remember doing this on a walk-in cooler, and I remember watching that um, uh, trying to get the charge correct with a sight glass and use subcooling. And I know that a lot of people in the refrigeration world don't use subcooling, but the way I was trained, I was trained on somebody who did industrial refrigeration systems as a specialty. Like that was what he did, and he came in and was teaching the class. That was his background. So he was worked on even as far as ammonia system. Like he had a very extensive background, and he did train that he used subcooling in a refrigeration system. Now we can debate whether that's correct or not later, but my point is like that was the day that this clicked, and why what I saw versus what I was told didn't match up. And I began my own journey at this point. And this is what 4 years into the trade for me, I guess. I began my own journey at that point, of trying to understand this for myself, taking readings, taking experiments. I would go run and do a call. I would charge it, and then I'd find myself having to come back to that unit at a later time because, um, like it had low charge symptoms, right? So we were doing stuff in peak summer, and as things cooled down later in the year, like we'd get a warranty call or a call back on it, and that I was realizing like you leak search the whole thing. There's no leaks anywhere, and you would think it's a leak, but anyway, after a, a lot of time on this, that's how I've rewired myself to realize what's actually happening. And as I got into chillers, it further reinforced this. Like chillers really further reinforced this for me, because we do have chillers that do operate based off of liquid level. A 19XR by Carrier is an example of this. More load, higher flow through the machine, higher condenser levels. That actually happens in a 19XR. We have, because that higher condenser levels more causes the float valve to raise up and float at a higher position, allowing more volume of flow through to the evaporator, which is at a higher load condition, moving more refrigerant through it at a higher volume. Right? So that's just like these are the things that further reinforced what I was seeing compared to what I was taught. Anyway, I get off on tangents really good. If you push the right button, I'll haul ass in a heartbeat. Okay. With higher loads, your head pressure will likely climb, but you should be able to maintain a decent liquid level across all loads, so your subcooling should go up. Does this make... Yeah, exactly. That's a very good That's a very good summary. If charge is correct, absolutely. Um, I like that, Michael. Dude, you're not hijacking the stream. This is what we're here to do. This is what we're here to do. So soul searching. Oh man, you guys. Okay, let me scroll up here. Um, IGBT, burn, reason, how to identify IGBT, amp. That York IGBT question. Yeah, IGBTs will burn out just from wear and tear. Now you could have an electrical issue. It surges the machine, power spike issues, whatever the case may be. But most of the failures I see are usually just from wear and tear. The silicon inside the IGBT, which is insulated gate bipolar transistor, the silicon wears down with time. It eventually just shorts out, fails, whatever, and it can quite literally explode or just come into a few different pieces at minimum. Um, so yeah, you may have had that. It could be compressor had an issue, caused a overcurrent spike. All of a sudden, the IGBT didn't catch it in time, blows it up. You could have had a brownout or a surge come through the grid, hits the IGBT or hits the power circuit, which affects the IGBT, causes a sudden spike in the DC bus, pops the IGBT, right? Those things can happen. In my experience, it's usually just due to wear and tear. That's the most common cause I've personally seen. But the others still exist. Okay, HVACR B7K. Chiller running normal condition, set point complete, but after 2 or 3 hours, direct set point increases 10 to 12 degree, and the motor load 60% to direct move full load 95. Normal condition, set point complete after 2 or 3 hours. I guess I don't understand. Oh, motor sound fully abnormal. What is the reason? Okay, I see the question. Motor sound. Yeah, so you're just hearing the motor load up. You said set point increases, so you've got a reset of some kind. That's what it sounds like. So okay, maybe you're not comfortable with what a reset is. Okay, so the core question is chiller comes on, it's running. After a few hours of runtime, the set point increases, and we see the motor load end up increasing in the process, which typically a reset, you'll have that because we want to see the machine derate and unload. Motor sounds fully, I guess, fully abnormal. And I don't know what machine this is. It could be a reset as to why the set point changed or the demand changed. If it's a process facility, it's possible that they may have transitioned processes. I really don't know. The more I think about that, I don't have quite enough information to go off of on that one. I'd really love to know, okay, what model of machine are we discussing? And just a little bit more about like what's happening and what the noise sounds like. There's a lot of noises these motors can make. So is it a bearing noise? Like just what kind of noise are we actually discussing? That would be helpful. Okay. Let's see. What questions are usually asked in a centrifugal chiller interview? It's a good question. Come on. All right. All right. So I'll take this from a standpoint of, okay, let's see. Yeah, questions that I can remember being asked and that I personally try to ask get into the actual technical. Now, I will say this. A lot of, especially managers, I find that a lot of the time you won't actually get asked technical questions. What you may be asked is, what have you worked on? What projects have you done? What machines do you know? You'll get a lot of those kind of questions, and they'll want answers to that in an interview where you're specifically maybe going in to focus on chillers for that company. So you'll get a lot of that. They just want to know what your background is, what your history is, and if you've got enough of a history to make them feel comfortable, then they'll move forward with you, whatever price pay scale y'all decide on. Now, I take things a step further personally because I know that just because you have worked on things doesn't mean you actually know how to work on those things. So, personally, if I'm looking at like an entry level guy into chillers or a mid level, can you explain to me what approach is? Can you explain to me some basic numbers of, okay, and many times I may coax this out of you because what I'll do is I'll intentionally start you on just having a chat and getting into different technical aspects, you know. So, well, what's one of your favorite service calls you ran? Well, why did that? Why did that one really stand out to you? And in that process, I'm going to get you to explain to me or indicate to me that you can tell me what the approach was and why that was having an issue, and you know, what are the different conditions and symptoms? How much did you see? And like as you just explain the service call to me, and then I may share some of my calls and throw some different machines out there that I've ran into and just see what kind of feedback do you have. Do you actually have the ability to talk on a technical level the way that I expect you to? And then that's going to change, right? So if you're entry level into chillers, then I'm more focused on, can you just discuss what basic approach and hydronics and things like that are? And as you're discussing some of your calls, I may have some questions of, well, you know, maybe you didn't tell me, hey, my approach was this and my TD was this. And so I may be like, well, when you saw that, what was your approach value? I expect to have an answer, right? Or at least indicate that you can answer and you would have checked that. Those are things I want to see that what you say you've done actually lines up with what you can actually do and know. That's how I'm going to try to coax that out. It won't be many times, it won't be literal direct questions. They may eventually turn into that, but a lot of time it won't be. A lot of times it will be just tell me what you've done. Okay, and in that process, through just natural conversation, I want you to indicate to me that you know the rest of this information. And then that same process ends up holding true even as I scale into larger machines. So if I'm expecting you to come in as a senior chiller tech on my team, I expect you to have the ability to understand centrifugals, maintenance procedures, a lot of just the fundamentals, that things that we have to do hundreds of times, thousands of times in a year on various machines, right? And you should have these things down verbatim in many cases, not necessarily all cases, but just can you show me through what you're discussing? Because if you can't express that in just a natural conversation, then you really show what you don't know to me. But like I said, that is how I've done it. That's how I hire a lot of my technicians when I was working as a operations manager. Like that is the process I'm going to put you through. But I find that most managers will take the approach of uh, just tell me what you've done, and then I'll base a decision off of how that sounds to me. And a lot of them aren't even qualified, sadly, to know any different, know any better, right? And it's not all companies. There's a lot of amazing managers out there. I'm just saying that some of these companies, even if you could talk technical, they probably couldn't. So, um, things to things to be able to discuss appropriately, right? Be able to explain approach, be able to explain oil separators, oil return circuits, be able to articulate some of your favorite service calls, because I know it's a very popular question. Um, like, what are just some that really stand out to you, and like really articulate those calls in a good way. That also indicates how well you can communicate with somebody else. The better you can explain that call to the manager, the more he has confidence that you can then explain that to a customer, which ultimately becomes a core problem. Like, can you get a customer to understand what you're saying? Um, yeah, that's that's my answer to that. Mm-hmm. Interview us, Holden. I have to sit a little. It's normal noise in 2025. Yeah. Hey, you've been through that interview process, Michael. You know what that's like. I mean, heck, I interviewed. Technically, that interview with you was before I was even a supervisor with that company. I was still operating as a senior tech at the time. So, but like, I had already adopted that kind of process from the previous company. And I find that interview process is a lot less offensive than just flat out asking you to explain something, especially for like experienced guys or guys that think they're experienced, because there's a lot of those. And like, they don't like being questioned, but then you put them in a position where they've got to explain something, and then they fall flat on their face, and then it's like, okay, well, here's what you actually understand then, right? So anyway, yeah, you've been through that process. You know what that's like. Screw medic. What's the voltage? It's exactly right. Yep. If you can show up with the right hat on, if you can show up with the right hat, you're automatically onboarded right there. Okay. I do know that there's quite a few questions I haven't got to here. I'm about to start saving those, and I will follow up on these in future streams. I apologize for just not being able to cover everything today. Let me. Okay, so we have a YK. On that YK, let me do some high levels on some of these just to give you something, and I'll do more in depth at a later time. So, we have a YK chiller oil return is not working properly. What is possible reasons? Okay, YK. So that's an eductor system. It has a solenoid valve that controls flow through the eductor from the evaporator. Is that solenoid valve working correctly? There's a filter dryer as well in that circuit between the solenoid and the evaporator. Is that filter dryer plugged up? That dryer is supposed to be changed annually. Has that actually happened anytime recent? If it hasn't, you might want to change that dryer out, or make sure that solenoid valve is working correctly, so that will open once the machine establishes operation. Like, you've got a stable operation. I forget the exact trigger point, but once you're stable, then it will open the solenoid valve to start oil recovery, but it will be closed as at first startup. So once the machine first comes on, that solenoid valve, expect that to be closed. Let's see. Make sure your liquid refrigerant level is correct, right? Really high level on the evaporator. So we're talking top of the sight glass. You won't bring back any oil, but you will bring back a whole lot of liquid refrigerant, and you may even see some icing on the oil sump, right? If you see conditions like that, you've got a high evaporator liquid level, You need to correct that, get that liquid level down. If your liquid level is too low in the evaporator, you'll actually get down below the oil recovery port on the side of the evap. So if you get down below that port, then there's just, all the eductor can do is draw in suction vapor. It can't draw in the liquid refrigerant oil mixture. So those are going to be some of the really high level things. Also make sure that you are feeding the the service valve is open on the condenser gas coming off the top of the condenser feeding into the eductor. That valve has to be open. So you need that high pressure gas coming in. You need to make sure that the service valve is opened on the eductor return line as well. So that's the same valve coming off the evaporator that feeds through that isolates the eductor circuit from the evaporator, separate from the solenoid valve. Those valves need to be open on the service line. So your service valves are open, your eductor or your filter dryer is in good condition, the solenoid valve is working, and the liquid level is correct. If all of those things are true, then you should be good and you should be functioning. But I would usually, with those, if the eductor system is not working, it's because one of those items is not correct. Evaporator liquid level, one of the valves, or the eductor filter, which is just it's a compression fitting filter dryer. It's all it is. So I don't think those are flared. I think those are the compression with an O-ring, if memory serves. Anyway, okay. I will save this question though, and I can do a much more in depth and draw it out and do stuff. So I've got a task sheet that I save these things in. So if I don't get to finish all the questions, I can at least save them and return to them later. Well, hold on, I have a question. There is a new feature on York YK Chiller Quick Start Chiller, start in 25 seconds. Yes. Can I know more about this feature? So the YK, or yeah, the York Chiller Quick Start, what that is doing is let's see. It's so that if the machine intermediately cycles off, it's able to spin back up really quickly, and it doesn't fully have to shut down completely and then start over. So during the coast down phase, if memory serves, it'll keep the VSD DC bus charged, and it won't immediately shut it off, the DC bus. It will keep it charged and go and allow the drive to then match the coast down speed of the motor and then ramp back up from there, instead of having to go to full stop, wait for coast down, wait for the off cycle, then recharge the DC bus, then come back online, right? So if I'm remembering correctly, that is the purpose of the of what the quick start is meant to do, is during that cycle. What I can do though is I'm going to save this, and I do want to go in and actually just reread that in the manual to make sure that I am remembering that correctly. So I do have that saved. That's something I can follow up on in the next stream, and I will go reread that to make sure that I'm explaining that correctly. Planning on starting my first career step working in chillers, and I want to know what the basics I need to know. Yeah, so I think we covered that in time when I enroll in the service training. Just been waiting until I got an opportunity to enroll in the training. Oh yeah, so you, in terms of the Chiller Academy, yeah, start off with the certification course. So at Chiller Academy, like, that is square one that you want to start off with. And I'm doing some major work on the service training program that I started, doing some major work to it, and I decided to close enrollments to that. So everybody that's already got access, you're going to continue to have access. It doesn't affect you. but I'm not taking on new enrollments until I get some projects done on that program. So in the meantime, like the certification course is the primary stop. Like if you really want to get your head around everything I'm discussing, that's where it's at. There, everything we've talked about today, all of that information, just the foundations you need is in that program. All right, make sure I'm not missing any others. Okay, we talked about that. Is the eductor nozzle clogged? It's supposed to be inspected and cleaned with that filter dryer. Right. Yep. Well, and that's if it's the external eductor. Okay, so keep in mind there's the internal and external eductor. The internal is in the sump. The external is mounted up on the frame. So keep that in mind with those the eductors on the YKs. There are two different versions. So searching my soul. Firefighter's going great. We've the first week or the end of November, we had several structure fires from people getting their lights and stuff up. But since then, it's gone well. We just had the county, our neighboring county, had a huge acreage burn off. It actually went really well. They didn't even have to call us in, which is great. But we were on standby for like a week to do the controlled burn that they were working on. So yeah, it's going really well though. Everybody on the departments is doing well for the most part. 60% on the intro course, and oh, thank you, thank you. The flow switch bypass module. Good one. Okay, MTT. Make the time for your family, for your spouse, for your kids. They really need you. We're not going to have the time. This industry is tough. Doesn't matter what you do. We've got to build habits to create this time. It's not just going to be there. If we don't force it, if we don't make it, if we don't be intentional with it, we're not going to have it. And at some point, we may not have them. Just something to keep in mind.